Welcome to Mass Transfer Operations lecture series.
Today we will discuss a very interesting topic, interface mass transfer. So what is interface mass transfer? The term interface represents two phases. An interface mass transfer means transfer of molecules from one phase to another. Let us try to understand this with the help of an example. What you see here is a vessel which is partly filled with water and partly filled with air. The blue dots here represent air molecules, and the violet dots here represents air molecules, and the blue dots here represent water. So this area is in liquid phase and the top part is in gas phase. Here I have shown some molecules of B, which is a representation for water molecules, because B is our second phase. Let us add some ammonia into the gas. So we have a gaseous mixture of ammonia and air. Here the air represents the ammonia molecules. So what will happen? The ammonia molecules which are present in the gaseous phase will diffuse into the liquid phase through the interface. The boundary separating the gas phase and the liquid phase is known as interface. To understand more, we need to familiarize some concepts. If it is an ideal gas system, we can use Raoult's law to know the partial pressure of the molecule that is transporting in the gas phase. For example, PA star, the partial pressure of A is equal to mole fraction of A in the liquid phase into the vapor pressure of pure A. So if we know the partial pressure of A, sorry, mole fraction of A in liquid phase, we can calculate the partial pressure of A in the gas phase. Similarly, by assuming that the system is in equilibrium. For non-ideal gas liquid system, we can use Henry's law, which relates the partial pressure of A in the gas phase and the mole fraction of A in the liquid phase. That is, PA star is equal to H into Xi, where H is Henry's law constant. So this can also be used to relate mole fraction of A in gas phase and liquid phase, because the partial pressure of A is directly proportional to the number of molecules of A present in the gas phase. So I can write Y star A is equal to M into Xa. We can also find a relation between partial pressure of A and concentration of A, such that PA star is equal to H prime into Ca, where Ca is the concentration of A in liquid phase, and M and H are Henry's law constant. So these are very few concepts which we will need to find the concentration and partial pressures. But anyway, let's get back to our system. We are considering a system which is partly filled with liquid and partly filled with gas, and we have added some molecules of ammonia into the air, which is at the top. Now the ammonia molecules will try to diffuse into the liquid phase. Let us try to model how the system behaves so that we can calculate the flux. The molecules of B are free to move in liquid phase. Similarly, air molecules are free to move in gas phase. But we have an interface here. How will the molecules behave when they are close to the interface? Let us try to model the system. The molecules of air which are close to the interface will try to diffuse into the liquid phase. But it is not easy for the molecules to diffuse. As a result, some of the molecules, air molecules which are present here, will form a stagnant film just above the interface. So a gas film is formed just above the interface, which are composed of air molecules which are at rest. We are assuming it like this. Similarly, the liquid molecules which are free to move in the bulk when it approaches the interface, will come to rest and form a liquid film just below the interface, like you see here. This area here represented by small lines is liquid film where the molecules are at rest. So we have a liquid film here and we have a gas film here. Now if the molecules of A need to diffuse from the bulk gas film to the bulk liquid film here, this will have to cross the gas film and the liquid film. In other way, the gas film will offer a resistance to mass transfer. Similarly, the liquid film will also offer a resistance to mass transfer. As a result, the molecule have to overcome these two resistances and reach the bulk liquid. So here I am going to represent the same system, but I am going to tilt it so that we can try to understand the concentration profile. Here the molecules of A, which is in the bulk gas phase, is trying to diffuse into the bulk liquid phase or into the liquid phase, and we have a gas film here, we have a liquid film here. If you see the concentration difference, obviously the concentration of A will be very high in the bulk gas phase, it will be very low in the bulk liquid phase, and what I have shown some 3 and 2 molecules here to understand, to let you know that there is a concentration difference existing, and as a result molecules are flowing or diffusing. So we can, since the molecules are free to move in the gas phase, I can assume that the concentration of A is uniform in the bulk gas phase, so which is represented by a straight line here, and let's say YAB with the mole fraction of A in the bulk gas phase. But what there is a resistance in the interface, so very few molecules will overcome the resistance and will reach the interface, that is this interface. So there will be a drop in concentration at the interface, and let us assume the concentration of A at the interface here is YAI. So the concentration difference existing here is YAB minus YAI, and as a result the molecules that were initially present at the bulk will diffuse through the gas film and reach the interface. So the concentration profile can be represented like this. Similarly, now what will happen at the interface? The molecules of A will diffuse into the liquid phase. The mole fraction of A in liquid phase is given by XAI. XAI value of XAI will depend on the value of YAI, and we can obtain XAI from this relation. YA, mole fraction in gas phase, is equal to M, a constant, into mole fraction in liquid phase. So here the mole fraction of A in liquid phase at the interface is XAI, and the molecules will now have to diffuse through the liquid film at the interface. It will have to overcome the resistance offered by the liquid film and reach the bulk phase. Once it reaches the bulk phase, the molecules are free to move. So you will have a concentration. We can assume that the concentration of A in the bulk phase is again uniform. So the mole fraction of A in the bulk liquid phase is XAB. So now what we have seen is molecules of A diffusing from the bulk gas phase to the bulk liquid phase through the interface, overcoming two resistance, a gas film resistance and a liquid film resistance. So the flux with which molecules diffuse can be represented as Na, and we can see the driving forces that will allow the molecules to transfer through the interface. Here the concentration difference existing between the boundaries of liquid film is YAB and YAI. So the concentration difference is YAB minus YAI at the gas film, and similarly the concentration or the mole fraction difference existing across the liquid film is XAI minus XAB. Here you can see from this equation the mole fraction in liquid phase can be written as a function of mole fraction in gas phase. So I can write the mole fraction on the gas phase, that is Ya, as a function of mole fraction in liquid phase Xa. So let's try to uh, find an equilibrium relationship by plotting YAI and XAI, that is plotting XAI in the interfacial concentration of A in liquid phase at the interface, and the mole fraction, interfacial concentration means mole fraction of A, YA, of in the interface at the gas filling. So how can we draw this graph? Let's, for that I'll do one thing. I'll just vary the concentration of A, or by vary the partial pressure of A in the gas phase by conducting, or by adding different amount of A into this system. Now by doing so, I can obtain different values of IAB. Correspondingly, I will have YAI interfacial concentration and XAI. So by increasing the number of experiments, I will get lot of values for YAI and XAI. I can plot all these graph and join the graph to get a relation between YAI and XAI. So any point in this graph will give you the corresponding interfacial concentration for the amount of A that was initially present. This information is needed to model the system. Okay, so now let's try to determine the interfacial concentration. I do not know what is YA and what is AI, what is the flux, but I have assumed certain terms, and let's try to solve this. Here, the flux with which molecules are moving, Na, is equal to Ky into concentration difference. That is, Ky is the mass transfer coefficient in gas phase. Ky into YAB minus YAA. I can also write in terms of mass transfer, in terms of mass transfer coefficient in liquid phase, that is Kx into XAI minus XAB, because XAI minus XAB is the mole fraction difference or concentration difference in the liquid film. So these are the two ways in which I can write the equation for flux. So, but since we have assumed the system to be in equilibrium and the operation is steady state, there is no accumulation in any of the film. So I can, these two quantities should be equal. So let's equate them, and so I'll get write YAB minus YAI by XA minus XAB is equal to KX by KI. Let's try to solve this graphically. So here I have plotted a graph between YAI and XAI. Let's plot a graph between mole fraction XA and mole fraction YA in X and Y axis respectively. The red graph that you see is the equilibrium interfacial concentrations. That is this one, obtained by like this by I have just explained the process. So here let's assume the red line to be the relation between XA and YA, the interfacial concentration. So let's consider one case. Let us assume assume that the concentration of A in the bulk gas phase is YAB. That is, here the concentration is YAB. So, and correspondingly the concentration of A in the bulk liquid phase, that is here, that is XAB. So you can plot XAB and YAB here. That will be this point. And we also know the interfacial concentration XAI and YAI. See, these are the interfacial concentration XA and YAI. So if I draw a straight line, the slope of the straight line will be Kx by Ki. So if we know the bulk, gas phase and liquid phase concentration of A, from the slope of this line, we can calculate the interfacial concentrations. But because we for that what more is required, we need to know what is Kx and what is Ky. These are mass transfer coefficient. In previous classes, we discussed different methods to find the mass transfer coefficient. You can use any correlation, you can use theories of mass transfer, you can use appropriate method to find the mass transfer coefficients. So if we know the mass transfer coefficient, from the ratio of them, we can calculate the slope, and equating that slope, we can calculate the interfacial mass transfer coefficients. Sorry, interfacial mole fractions. Okay, I hope that is clear. Now I'm going to introduce another concept known as overall mass transfer coefficient. I used to discuss flux is proportional to driving force. So through the gas film, molecules are diffusing. Through the liquid film, the molecules are diffusing. What is the flux? That is, flux here is Na. What is the driving force? Here, YAI minus XAI. YAB minus YAI. That is in the liquid film. So the flux is proportional to the driving force. So here again we have a concentration difference. That is XAI minus XAB. But what is the overall driving force? The overall driving force is the overall concentration difference, which is expressed as small fraction here. That is YAB minus XAB. So I can write flux in terms of overall driving force also. So let's write that. Here overall driving force is YAB minus XAB. And we know the liquid phase mole fraction is a function of gas phase mass fraction. So I can replace this XAB with a term known as Y star AB. From this relation, I can write the corresponding Y star AB. So the reason I'm going to tell this, I'm going to express concentration in terms of Y star AB. So I can write flux is equal to Ky into YAB minus Y star AB. What I have done is, instead of XAB, using this relation, I use the corresponding Y star AB, or corresponding instead of XAB, I am just using Y star AB. So I can write flux Na as capital Ky into YAB minus Y star AB. The term capital Ky here is called overall mass transfer coefficient. This is a constant. Whatever values we use, this constant will absorb, and so the proportionality exists, and we will be able to calculate the actual value of flux. It doesn't matter if we use XAB or Y star AB. To the constant of proportionality will absorb the difference. So here Na is equal to capital Ky into YAB minus Y star AB, and the term capital Ky is called overall mass transfer coefficient. So let's try to find what is this Ky. How can we find the value for overall mass transfer coefficient if we know individual mass transfer coefficient Kx and Ky? We cannot find the overall mass transfer coefficient using any correlations or any methods that we have discussed in last lectures. So here let's try to find an expression for Ky using what we already know. We know Na is equal to Ky into YAB minus YAI, which is equal to Kx into XAI minus XAB, which is again equal to capital Ky into YAB minus Y star. From this expression, we can write Na by Ky, Na by Kx, and Na by capital Ky. Let's try to solve this. So here, YABY minus Y star AB is equal to YAB minus YAI plus YAI minus Y star AB. I added and subtracted YAI. So now let's group things together. YAB minus YAI, because we know what is YAB minus YAI. See here there is a name missing. Please add that. So in plus, and in the second part I am going to multiply and divide by XAI minus XAB, because again we know what is XAI minus XAB. So let's write YAB minus YAI plus YAI minus Y star AB by XAI minus XAB, again XAB into XAI minus XAB. So what is XAI minus XAB? It is Na by Kx. But if you look at this plot, YAI minus Y star AB by XAI minus XAB is the slope of the line connecting these 2 points. This point here is the interfacial point corresponding to interfacial mole fractions, and here this point here is Y star AB comma XAB. XAB is the mole fraction of A in the bulk phase, and Y star AB is the corresponding concentration in gas phase. So from the slope we can replace the term YAI minus Y star AB by XAI minus XAB as by log m dash. So let's substitute for known quantities. YAB minus Y star AB is equal to NA by KY is equal to NA by small ky plus m dash into NA by Kx. And I am going to introduce the concept of resistance now. The quantity 1 by K, I can cancel off Na from all the three, and I can write 1 by Ky is equal to 1 by small ky plus m dash by Kx. The quantity 1 by Ky is equal to is known as gas phase mass transfer resistance. The quantity 1 by small ky is called individual gas phase mass transfer resistance, and m dash by Kx is again individual liquid phase mass transfer resistance. In other words, 1 by ky, small ky is the gas film resistance. But why do I say it is the resistance? Because I know flux is proportional to driving force. So I can write flux is equal to driving force by resistance. Here flux Na is equal to ky into YAB minus YAI. That is YAB minus YAI divided by AI divided by 1 by Ki. So the quantity that is present in the denominator is 1 by Ki, and that is the resistance offered for mass transfer across the concentration difference. Here YAB minus YAI. So here I can say 1 by Ki is the individual gas phase mass transfer resistance or resistance in liquid in gas film. Similarly, m dash by Kx is the resistance offered in the liquid film, or I can say it is individual liquid phase mass transfer resistance. So, and if I consider this equation, Na overall flux is equal to constant Ky overall mass transfer coefficient into YAB minus Y star AB. That is Na is equal to YAB minus Y star AB divided by 1 by Ki. So similarly, I can say the term 1 by Ky is the overall resistance. So here we have 1 by Ki, and hence 1 by Ki is the Ky is the overall gas phase mass transfer resistance, and these two are individual mass transfer resistance. So sum of these two individual resistance will give you the value for overall mass transfer resistance.